Okay, today's speaker is Stefano Stefano is a research scientist at the Norwegian Institute of Bioeconomy Research. Doing research in proximal laser scanning, I guess that means TLS, and deep learning for capturing individual tree properties and applying this information to forest management. I ran into him as a keynote speaker at Sylvia Laser in London earlier this year, and I thought he gave absolutely brilliant keynote. And immediately ran to him and said, "Can you please give us a talk?" And I'm so happy that he agreed. So I'm looking forward to I think to a beautiful talk. Actually, the first slide already is beautiful. So the rest will be amazing as well. So thank you so much, Stefano. It's all yours.
Yeah, thanks a lot for the invitation. And yes, it was a pleasure to meet you in person at Sylvie Laser at UCL. So today I thought of speaking a little bit about similar things that I had been speaking during the keynote, but I guess maybe many in the audience were present there. And a little bit some of the progress that we've made in the past couple of months. So the idea and the context that we're in, we deal with. I am originally a forester, and then specialized in forest remote sensing, and we deal with a lot of point cloud data coming from primarily laser scanning instruments that can be mounted either on aircrafts, on drones, or can be terrestrial. And this gives us this very fantastic representation of the forest. As you see, like, for example, here, a sample of trees that we have, very detailed representation of trees. And then we want to use that information to manage our forests in a more sustainable and more efficient way. And a bit the clue here is that we, until now, these point clouds have been used a little bit in a way of extracting some sort of metrics that could be related to key forestry parameters. Now we're moving closer, and so basically before the unit was like a pixel, let's say, and now we're moving more and more towards individual tree forest type of management, both because society requires a more closer to nature type of forest management, but also forest managers can benefit from that information. And this is largely work that I have been doing within Smart Forest, which is a 8-year research program that we have here at NIBIO on all kinds of aspects related to forest and technology and sensor data and AI related to forest. So when we look at these scans, suddenly we have really a stunning representation of the forest. And you look at this data and you fall in love. And that's what happened to me. And I have to say, it's easy to sell this data because it's just like so visual. And until now, our eyes were able to appreciate this level of detail and this level of information that it's held by these point clouds. But we hadn't been able really to tap into the full potential of this data because we didn't quite have the tools. But for example, what you're seeing here, it's an oak, just like from a weird angle. But just like you see the sheer level of detail, you see like some sort of details of the bark and the fine branches. So it's really, really, really beautiful data to look at. And it can tell us much about very different aspects of the forest, including forest growth. So we can kind of monitor how different trees grow and different climatic aspects that affect the growth, or micro habitat aspects that modify growth. It can tell us about wood quality, which is something that our kind of industrial partners are very interested in. They want to know from standing forest, what is the quality of a certain saw log, that what kind of end products can they derive from that, and so on. And having that information while the tree is standing, of course, can really boost the efficiency, because they can know exactly which link the demand with the offer that the forest has. It can also tell us very much information about biodiversity. So we have clear representation of the forest structure, but not only, we have also information about the understory and other aspects of the forest that can be very valuable when wanting to manage for biodiversity. And it tells us, of course, also about the health of the forest. And so all of this information is encapsulated in these point clouds. Our eyes look at this data, and we immediately can see here that there's a tree that has fallen down. So something has happened. But until now, we haven't been able to really look into it because of the lack of methods. And then when you see all of this information about individual trees, then you can start to bring it all together and start to see the whole forest. So that's why I'm talking about seeing the forest through the trees, because it's the combination of the multitude of trees that come together and then form the community, but you have information for each individual. And that, of course, gives you a much better understanding of the whole community. So when we talk about point clouds and forest information, this is what the type of data that we get from the scanners. Very nice. We see very much detail. And we want to convert this information into something that it's useful both for forest management, so something that gives us information about the value of the forest in terms of timber products. It tells us something about recreation. It tells us something about biodiversity, so that we can, in the end, establish personalized treatment schedules for each tree, depending on what we want to maximize. And at the same time, we can also use this information to support large-scale monitoring programs. So, for example, we have a EU project where we're establishing a first forest monitoring network throughout Europe. There, these high-density point clouds are also one key enabler to allow to collect good ground in situ data to calibrate then satellite or other remote sensing data products for calibration and validation. So when we start this quest of trying to get this information from this point cloud, a first step is to just kind of get some semantic understanding. So we could, like a very basic operation that has typically done within the LiDAR community is the LiDAR forestry community is separating the trees from the ground, which then allows us to also compute the individual tree height. So that is the first step. So here I will just show you a little bit conceptually the steps that are needed to reach that level of information that we're after. So we want to have some information about the semantics. Very important, we need the information about the individuals. So we need to split this into each separate instance. So it becomes a bit of an instance segmentation problem. And when we put the semantic and the instance segmentation, then we have some sort of panoptic segmentation problem. And then for each of those individual trees that we've identified and located, we can start to talk in a way with these trees and extract information and analytics that help us in better managing that specific tree. So as an example, we can get information about the species, the height, what is the volume of the crown, what is, of course, the latitude, longitude, health, the social status. But you can see that we can, the list here is not comprehensive at all. There's a multitude of variables that really are key in knowing how to then manage that tree. And they can be fed to optimization, to some optimization that actually can determine, depending on the end goal, whether it's that forest is a productive forest for timber, or one wants to aim towards conservation. And then one can define different silvicultural treatments at the individual tree. So for example, this tree, let's say we want to keep it alive there because it has an important biological value. So this is really the end goal, to start to have these tree lists with all of these attributes associated. Also, when we look at these point clouds, generally we see trees, right? Because that is the dominant part. It's really powerful for our eyes. And we see the trees, definitely. But we also have an amount of information related to the forest floor and the understory vegetation and whatever lies beneath the trees, the tree canopy. And therefore, it is important that we start to treat this, that we typically has considered this as kind of something to remove, as actually like a source of information. So we can start to take the ground and start to split it into different semantic classes, such as the ground itself, adding some rocks, which can be useful, for example, when trying to plan autonomous navigation schemes through the forest and we want to know what obstacles there are in the forest. But also we can start to add what is the dead lying wood. What, like, this has an important value under for biodiversity. It's an important indicator for biodiversity. So, but we haven't quite been able to map it yet. So we want to be able to do that, and as well as the lower vegetation. So you can see that out of like something that before was considered something to throw away because we only needed to look at trees, suddenly we can start to extract a lot of information that is actually valuable when we start to include more and more biodiversity goals in the management of the forest. So as I said before, until now, we really lacked the tools to be able to take the complexity of data, that 3D complex structure of the data, and bring it to extract meaningful information and in an efficient way. Past 3-4 years, we started shifting towards more deep learning methods to look at these things, and since then we are stuck there because we've just seen that the improvement was so large compared to what we had before. So we are kind of delving into a new world, which is not really that new. Like when you look at the across many different disciplines, but within the forestry world, this hadn't been really applied very much. And in general, also within the machine learning world, the point cloud, deep learning and 3D deep learning, it is still also like studied like in a rather limited way, especially when we go towards some of the tasks that I'll show you later. So the deep learning in this case really becomes the enabler that the Google Translate for us to tell us what these trees have to tell, the information about these trees. So one example, just to show you a little bit, like the forestry sector, how it has moved through the world of deep learning. It's something that came relatively late. So one of the most, I think, important examples is this study by Sean Krasansky, which developed a sensor and platform semantic segmentation model that dealt directly with point clouds. And what was very interesting, and I think what was very appealing for the rest of the community is that this model could transfer very well to new data sets. So as an example, Phil Wilkes, he took that model without even retraining. That model was trained somewhere in some forest in Australia and Tasmania. And Phil started to apply it in French Guiana, in the US, and in Malaysia, and in the UK. So very different forest types. And suddenly that model was very transferable, something that we hadn't quite seen before in the forestry world, where we are used to, in every area we go, collect calibration data and do all of that very expensive process data. So this was something I think quite interesting. And since then, more and more people, more and more researchers started focusing on this problem of semantic segmentation, which is great. However, it doesn't solve the whole problem. One of the major limitations in the development of all of the deep learning world in the forest remote sensing world has been really the lack of availability of data sets. So differently than many other fields, especially like computer science, where there is much more widespread sharing of data and making these data sets available for the broader community to benchmark, to track progress. In the forestry world, there has typically been people sitting with data on their own hard drives, still a little bit old school. But we're now starting to see a bit of a shift towards something that is a bit more open and something that is a bit more efficient in terms of allowing us to track our progress on the development of these methods that we're after. So if you want to know something more, there's a short conference paper that Emily led last year on some of these issues and the status in the forestry world. And as one of the main drawbacks of how things had been done until now is the fact that people were tailoring methods to their data sets. So then the methods were hardly transferable to new data sets, and therefore the progress has been very slow. So in an attempt to gap some of these limitations and to advance our ability to derive useful information from this 3D forest scene, at NIBIO we established two important benchmark datasets. The first one is this 4-instance dataset that is for point cloud semantic and instance segmentation, and the other one, the 4-species, which is has been it's a dataset that has been compiled within the 3D for Ecotech coast action. So a lot of contributors there from the cost action and also beyond that provided data, and that is for species classification. So 3 species classification based on point clouds. So I will show you now a little bit like what these two data sets are about and some of the work that has been done, some of the initial work that has been done to define baselines and what is the current state of the art within these two data sets. So the 4-instance data, it's a data set that has been compiled from different regions around the world, and it's composed of drone laser scanning data. So quite detailed airborne data. What's the clue here is that we're talking about airborne data, meaning that the laser pulses, I'm not entirely sure how much you guys know about laser scanning technology, or if I should go more in detail, please let me know. Yeah, okay, good. No, but the main clue here is that terrestrial and airborne point clouds, they differ very much. So airborne point clouds, the laser beams are often intercepted by the crowns. So these point clouds are generally sparser towards the ground, whereas terrestrial point clouds are the opposite, right? Sparser towards the top, denser towards the bottom. In this case, we collected these different data sets, some from Norway, Czech Republic, Austria, Australia, and New Zealand. And these have been manually segmented, really painful work, because differently than urban data sets or indoor data sets, 3D indoor or urban scenes, where the instances are clearly separated. In this case, we're talking about trees that very often have the crowns that are intertwined. And so even from a machine learning perspective, this brings it to the extreme of complexity in terms of trying to split these trees aside. And we have about a total of 1,000 trees. Yes, and I meant, sorry, I didn't say that there is both the instance annotation and there's the semantic annotation. The semantic annotation splits the tree into stem, branches, and leaves, and ground, of course. And some of the initial work that has been done on this, there was initially a paper from Straucher et al., who applied a YOLO v5, so basically a image segmentation algorithm to a bird's eye view representation of the forest, where you basically, what the colors that you see here are basically height above ground. The warmer, the taller, at different resolutions. And we found that that was actually outperforming already previous methods, but in a way it was suboptimal. It was not really dealing directly with the point cloud, it was dealing with image representation, projections of the point cloud. Moving forward with EPH, we have been working on an implementation of point group. I will describe a little bit more in detail point group later. And you see that we clearly improved that basic configuration of point group. And that was the beginning that we then further developed on this point group for panoptic segmentation of these point clouds. So how this panoptic segmentation work in point group is that we have this backbone network, which is generally like a UNet structured network with the two heads. One is a semantic branch, and one we have an offset branch, where the semantic branch provides general semantic understanding of the point cloud. So a semantic segmentation, which is then used to cluster into different instances using the offset between these instances. And this, the advantage of this method is that it is an end-to-end method. It is trained end-to-end. So differently than some of the few examples that have been proposed before, they were a bit like algorithmic pipelines composed of different models and different things. This is trained end-to-end. So this was the original implementation from 2020. And then what, so what Binbing Chang did in 2023, she replaced the backbone with the Minkowski engine implementation of sparse voxel CNN. So it's a convolutional neural network happening for voxels. And then expanded to a third branch, which basically implements a 5-dimensional clustering of the embedding space, what's particularly important is that the loss function used there is used to basically minimize the distance between the points within one tree and maximize the distance between the points to neighboring trees. So basically, it brings the center of all the points them towards a centroid or a center of gravity of that tree. So based on these implementations, we saw some improvements, and then we took that basic idea, and then we wanted to know, okay, how does it work if we want to make this model fully like platform and sensor agnostic? So we want a model that can work on terrestrial data as well as data. And the reason is that very often we end up in this situation that you might have data sets that are in between, that you don't really know which method should be used. And at the same time, we see that our human eye is clearly able to tell that a tree is a tree independently whether it's terrestrial data or if it's airborne data. So we took the 4 instance data that I mentioned before, and we took some mobile laser scanning data that was also instance labeled. We sparsified these in a very naive way by just like randomly sampling points to reduce it to very sparse point clouds. And these sparsity levels, they are representative of different types of data that one might get either from airborne platforms or airborne platforms at different altitudes and so on. The reason, so basically, the further you go to the right here, the more the impact of the, so if one can predict instances, do instance segmentation on these point clouds, then that would be something that would be applicable on a very large scale globally. So we took these different data sets and we combined it into different scenarios and different, we could call them, it's some sort of augmentation strategy. So different degree of augmentation. And then we benchmarked against some data sets that are publicly available, so they were not used in the training. So the Witham Woods, the Tree Learn, this is from Germany, so this is from the UK. I guess quite close to where you guys are. This is here in Norway, so some boreal forest. This is in Austria, this for instance again, and then we also compared to the very sparse data. And then we evaluated this at the point at the tree level, and then within a tree we defined true positives, false negatives, and false positives at the point level, and then try to understand the performance at different heights in the canopy. And the results really showed us that this method could be applied to some of the densest point clouds, as well as to some of the fairly sparse point clouds that we had. I didn't include here now all the figures, but what was, I think, particularly interesting is that when I took this model and then applied it to real data that we have, so the first row, what you see up here is, for example, a data set that was collected with a helicopter. So flying rather low, but we see that our model could predict quite well on this data. And also what is really important and what is really groundbreaking that previous method hadn't been that great on is to predict and segment trees that are under the canopy. Before using this bird's eye view approach, the top canopy would basically, that would be the only thing you'd be seeing. So really we are advancing our ability to detect the smaller trees, as you see also in these lower rows and other types of data. So this, I think, was quite a groundbreaking step for us, because once we can go at individual tree level, then we can start to, we have already in place a lot of methods to extract the information that we're after. When we compare basically the state of the art, we see that we have improved the state of the art, but again, this is another manuscript that it's in preparation. We still have to a little bit see, so let's not use these final values as the results, but we see that definitely there is a big jump in the state of the art. And then the three species effort. So here we, within the 3D for Ecotech cost action and smart forest, we compiled this data set. So large number of contributors around Europe and around Canada and Australia and the US. So many contributors that helped out. Might recognize Emily there. And here we were actually able to compile 20,000 trees covering about 30 species. And all of these trees, keep in mind that all of these trees are actually manually segmented, which is a really, really time-consuming task. So it's quite a nice data set. And the idea is to, from these, to be able to predict species. So to each of the trees, we have a species associated. So species classification, and we hope to have it, to do it in a sensor and platform agnostic way, in the sense that given the same model, we can apply it to terrestrial and airborne data and anything in between. This is the distribution of the data, unsurprisingly skewed, but that's just how nature is. But I think actually that initially it seemed like a challenge, but in the end it turned out to be an important part of the competition that we ran on this data, because people had to develop methods that were robust to the imbalance of the data, the input data. We split it into dev and test data. And then we had a go with some people that are participating in the cost action. You might recognize Matt Allen there. Always joke about his GitHub picture, the unicorn. And within about 5-6 months, we had several contributions, some of which also had several iterations of several submissions. And you can see that, so here basically we have point cloud based methods, so PointNet++, MinkNet, MLP Mixer, Point Augment, whereas here we have image based methods. So not always when dealing with point clouds we need to actually deal with the point cloud, but we can deal with projections of the point cloud. So that's how actually these top scoring methods worked. I do not want to conclude on, or I'm not really interested in concluding is point cloud methods better than image methods. I don't think that's the particularly interesting aspect, but I think the interesting aspect was to show a little bit the forestry community how to perform proper benchmarking on this AI methods, and to really be able to track the progress. So when we look at this graph, based on the F1 score, we could really track how well we did and the improvement in the state of the art. And this is something that it would have taken us maybe 5 years before, because it would have just had to be, we would have had to understand this through replication rather than benchmarking on a common data set. So I think that was a very, very nice experience, and I think we'll have to soon write this one up. Yeah, and the method that won the competition was this multi-view approach, which, given a point cloud, that generates different viewpoints and just takes snapshots of that point cloud converts them into images, and so it was inspired by the method published by Matt Allen last year. It just added a little bit to it with, for example, a close-up view of the trunk, for example, that could be helpful to determine the species. So all of this went. This was the end of this internal competition, and now we hope to write it up, publish the data, and then hopefully people can advance the state of the art even further. And hopefully we can see these point cloud methods, I think, running up the state of the art. This was a confusion matrix for the 30 species that we had. So we can see that actually it worked fairly well. For some species, things were a little bit strange. Some of the classes were poorly represented in the data, so it's not surprising. And also we could see that the performance of, for example, the orange, which is the winning method, was fairly consistent throughout the data sets. And that, so that was something quite encouraging, indicating that, yes, we can perhaps have a model that can deal with all of these different sources of data. And also the accuracy, this is 2-meter height bins. So it's basically telling you that the distribution of tree heights that we had in the test data. And you can see that when we are above 4 meters, trees that are taller than 4 meters, the accuracy was fairly consistent. Yes, so all of this is or will be published as open data with training and training and test splits. So one can then take and run experiments. So if you ever get some master thesis or someone interested in delving in the world of point clouds, you're very welcome to either just download the data or contact us if you want to also work on some of the latest benchmark works that we're doing. Yeah, so I think that was all from me, and I'm happy to take any questions if you have.
Thank you. We have time for questions. Yeah, I know.
Thank you so much for that tour de force through so many techniques. It's fascinating to see that it was actually the simplest technique that discarded lots and lots of point data that was the most effective. So you're effectively just taking a few snapshots from different perspectives and then using that to train the classifier. I didn't quite get an intuition for why the 3D models underperform so much. Is it just a matter of still finding something more accurate, or was it just not? Is it some fundamental limitation, you think, in the way this is being approached?
Well, so first of all, initially the point cloud methods were lagging behind quite a lot. But then there was this latest PointNet++ implementation, which included several augmentations and things, which bumped up the point cloud methods fairly close to the image-based methods. But what I suspect is just a little bit that the image-based methods have been advancing for so long. So in a way, 3D deep learning is lagging a little bit behind, I think, compared to the image-based deep learning. And I suspect that would be the one of the root causes. I wouldn't know nowadays if one was to go into the transformer world, like, and self-supervised transformer world, like how this would look now. So I'd be curious to see some latest point cloud implementations.
I've seen papers fly by on AR and VR based self-supervised learning. So, and those are obviously much more in the three-dimensional space than normal image recognition. But I haven't looked into the papers, but it's a fascinating direction of travel.
Yeah.
Thank you. Yeah, David.
Thanks for the talk, really interesting. I work with airborne ALS, where we're flying quite a lot higher than you. We've got much lower point cloud densities. I think you're in helicopter, for example, 600 points per meter squared, and we're lucky 30, something like that from our aircraft. But of course, we can cover much larger areas and provide information that landholders want for us. I just wondered if you thinned your data cloud even more down to the sort of levels which an aircraft get a kilometer or two up would have, how it worked at that sort of scale.
Yeah, so one of the main limitations, right, is the lack of suitable benchmark. I guess you actually were recently involved in a paper where you did benchmark this against like individual tree segmentation methods for airborne point clouds. I do not know exactly how it would work, but we did thin it to the level of what was it? The lower end was about 10 points per square meter, which I guess would be somewhat representative of that sort of. Yeah. So if you look here, those point clouds could those be representative?
Just couldn't see it on this.
Yeah, no, because it's very difficult to see this. Yeah, with the 10 points per square meter, but I guess that would be similar sort of resolution to what you might have. My general gut feeling is that also with those methods, we are doing better with the understory trees. And the reason is that we're not limited by this canopy height model detection, which it's inherently like removes all of the lower vegetation. So I would be very interesting to try. We in Scandinavia now, we start to have a lot of these data sets that are in the order of, let's say 100 to 600, up to 1,000 points per square meter. And these are kind of collected operationally. So I think that would be the optimum range for this type of method. But I wouldn't be surprised if we actually start to do fairly okay also with 50, 30. When we start to get to 10, things start to get very sparse. So there are challenges, yeah.
Thank you for the talk. I'm wondering, like in your database, for each you have the RGB information for your segmentations. My question, first question.
Sorry, I didn't hear very well.
So like in your database of the 3D point clouds, do you have also the RGB information associated with each individual point? Do you use those RGB information for your segmentation?
No, not really. Well, we have it for some point cloud, but the reason is that the RGB is generally given like based on the some images that are associated with the point clouds, and in that case, the color information is not that great. It's okay for perhaps the top of the canopy, but once you start getting lower in the canopy, it's not as meaningful. Perhaps what we're starting to see now is multispectral LiDAR systems that start to have that sort of information, but we haven't quite worked with that. What we have is like the typical LiDAR information on return number and intensity and this type of traditional LiDAR variable. Yeah.
I see. Another quick question is that more about the high levels. Let's say you mentioned the application forest management. Let's say I'm a forest manager. I have like 100 hectares of lands. I want to estimate the biomass of this 100 hectares of lands using your method. What kind of data I need and how much should I cost for estimating those biomass?
We hope that you can get yourself something like on this lower end here, which would be a drone laser scanner, which nowadays they can get fancy, but they can be also of some sort of consumer grade. So this is a DJI product. The data isn't that great, I have to say. So you will degrade the performance, but this would be something that you can do yourself. This is something that you might need a company to do for you. So yeah, it depends a little bit what your budget is. Like generally up here in Scandinavia, we deal with large forest owners. So they hire a company with an aircraft or a helicopter and go and fly 1,000,000 hectares, right? So then that would be the situation, and that's how the cost is kind of taken down here.
Thank you again for an amazing talk. I'm just curious, you were talking about mapping the undergrowth and the forest floor more and more. Could you say something about the main challenges of why that's more difficult than the trees?
That is more challenging, well, simply because it's really difficult to get your hands on decently labeled datasets. So first of all, they don't exist. So that's what we're working on. Beyond that, I don't know. I don't honestly think that it's a massive challenge. I think that the signal is clearly there. You like, if I am able to label this data, which means that should be something definitely that one can automatically use to predict these features. One important aspect is, again, the density of the data. Do we want to bring this airborne, or do we want to just, are we happy with just like terrestrial? So should we sparsify this, and like how does that look? Because when we start to sparsify these data sets, suddenly like their scope increases massively. So we can suddenly use it at scale. Whereas this, what you see here, it's a very beautiful picture, but it's on a 1 hectare scale, right? So
yeah, let's see, is anybody else? Yeah, there we go.
Can I follow up on that one? Because if I can tempt Emily to Scotland next year, we'll be doing some measurements of coarse woody debris on the forest floor. Because
Hi, David. I'm listening in case you're going to insult me.
Man, I didn't know that. When I tempt Emily up to Scotland next year. When you said quality data for measure of the field data, what do you think constitutes quality here? I mean, the RSPB, our partner up there, goes and measures volumes of coarse woody debris, but they won't have the individual trees mapped out on the ground, I don't think. I just wonder whether you've had any thoughts on what actually we need to train the AI to be able to predict them from, in our case, airborne datasets.
So in terms of quality of data, I mean, both the labeling of the point cloud data, which of course in airborne datasets, it's hardly possible because things are so sparse that it's very difficult to see things. So one has to go to the terrestrial data and start to leverage that terrestrial data to build models that are applicable to airborne data. So I think that's the fantastic step, that we can start to leverage the availability of all of these terrestrial data sets to suddenly start to fit a model that is able to transfer to airborne, but also is in the ground truth data. So in this Pathfinder project, in this EU project where we are looking at the European-wide monitoring program, I was developing some techie plots, and there what we did is, for example, to map each of the logs in the field, including also variables such as decay status. So like knife and like going through the wood and kind of adding some qualitative information. So it comes both from a virtual side, but also from the field side. So I think it's merging those two and starting to collect in situ data that is fully mapped to point cloud data. Does it answer? the question.
Yes, and hello, Emily.
Any other questions? Is anybody online who'd like to ask a question? You can unmute yourself and ask now. For quite a few of you. Okay, I don't. Yeah, go ahead. Yeah.
Like in your four species, are you aware of any like rare species but holds important economic or ecological values?
Sorry, could you repeat the question? I didn't quite get.
In your four species database, are you aware of any like rare species or not common thing species, but they hold important economic or like ecological values?
Yes, no. Whether those are well represented in the data, I'm not entirely sure. What I know is the main like dominant species throughout Europe, those are well represented throughout the data. Those being, let's say, beech and Norway spruce and Scots pine, and but it is not a fully comprehensive set of tree species. It's things that have been sourced based on either openly available data sets or people that had this data on their hard drives and shared it. So we are looking also into a version 2 of this data. After Sylvie Laser, there were a lot of people, I have this data, like, when are we doing version 2? And so first I would like to maybe wrap up version 1, and then hopefully we start to grow in terms of number of trees, those classes that are a bit underrepresented, and yeah, especially maybe some trees that have particular value.
Okay, let me ask.
Yeah, I'm hoping to get from a general model for different sensing technologies. Like, why would you do that as opposed to package specialized models together and include a flag for your given data set?
The reason is that flag is not always very clear what flag one should put, because suddenly we start to have data sets that are quite close to each other. And so in terms of versatility of the model, I think that's what we explored here. It was like how versatile these models are. I agree with you that maybe at some point, if I know that I only deal with TLS data, perhaps I'd train a model just using TLS data. However, where I work, we work on all of these different, let's say, data modalities, right? Or data resolution levels. So it gets very difficult sometimes to put an exact flag on what is what. But also, like, maybe to highlight that the key interesting thing there was a little bit what I was saying before to David, that we can start to leverage these very detailed point clouds from terrestrial or drone laser scanning, that they're very easy to annotate because we see features very well there. So they're okay to annotate those. And we can take those and train models that can transfer to sparse data that would be otherwise not possible to annotate. So I think that maybe is the major contribution. Yes, we can have the fully agnostic model, but especially we can start to go into the low end of the scale where otherwise it's very, very hard to get good training data.
Okay, let me ask the last question almost out of time. So your work has been focused mostly on instance segmentation, if I understand it correctly, but obviously this is the first part of many other downstream tasks that we would use instance segmentation for. So what kind of tasks do you think your data set would be useful, could be useful for, whatever you use it for, that would be not just segmentation, because segmentation is just kind of a helper to do something more interesting. So could you kind of speculate on the kinds of things one would wish to use with this data for?
Yeah, the benchmark data sets or
Any of this work really, because if you're trying to get a very good segment, let's say 100% accurate segmentation, what could you do with it?
yeah. So the instant segmentation is a long-standing problem. It's about like 10 years, no, 20 years that people have been working on it. It started like, in the end of the 90s. There were some of the first examples of LiDAR and individual tree segmentation. Yet, until now, there hasn't really been like big steps in the state of the art. We've been pretty much at the same level, just like always under detecting trees that are under the canopy. And so in the end, it didn't really become a very operational tool. So really, for us, solving that problem, like on the other end, like having this individual tree information, as you said, opens a lot of downstream tasks. So it was really a bottleneck. So for us on the forestry side, it's not a particularly interesting topic, but it's a very, very interesting tool to have because suddenly, if we have the individual tree, then I can plug it into the tree species detector. So then it tells me about the species, and then I can do other tasks. For example, we've been working on the modeling of individual tree height growth. So given one of these point clouds of this tree, we're able to reconstruct like 60, 70 years of height growth of that tree based on the detection of some kind of branching patterns and branching characteristics. And as I said, one very important one that the forest industry is very interested in is wood quality. But like more and more, what they're really asking us is to use these point clouds to identify areas that should be retained from harvesting for biodiversity purposes. So that is really like one of the, I think, important and very difficult tasks that we are dreaming of, let's say, like many.
Great, thank you very much. I guess we are at the end of our time, so let's thank Safaran. Thank you.
Thank you very much.